Hello, everybody. My name is Andrew Young, and I'm going to talk to you about a random little experiment with some Raspberry Pis today. No, that's actually not true. I'm going to talk about Astra. It's a little bigger. So, yeah, my name is Andrew Young. I'm a computer scientist at Sandia National Laboratories. I'm giving this presentation. However, there's a large team behind this, so don't think I'm the only one playing around with this big machine. Specifically, Jim Laros, Kevin Pedretti, and Cy Hammond really wish they could be here. So to build a machine like this, it takes a huge effort and a whole lot of collaboration across not only the DOE and the Tri-Labs, but also with some of our key partners. Many people may even be here and see their name up there, hopefully. HPE, Marvell, ARM, and Linaro. Seriously, thank you guys. This is a significant effort. This is not just me. You guys are blessed enough to have me here talk about this. So. We also got a lot of permission to use some pictures, so I'm going to try and have some fun, and that's sort of just the core Sandia team on this. So I've been talking about Astra here at Linaro for, I don't know, 18 months now probably. So I'm hoping to sort of focus on some of our latest and greatest and sort of try to give you a full, complete picture of where we're at and what we've been up to and that sort of thing. So I'm going to quickly go over sort of the overview of Astra. This may be boring if you guys have heard some of this stuff before, but if not, just in case, we'll talk to you a little bit about what Astra is. I'm going to try and focus a little bit on the software stack as well, because I think that's really valuable and interesting for a lot of people here, hopefully. And then also, we can share some application results, and these are not just mini apps, so hopefully this will be of interest. And then we're going to kind of have a quick discussion about where are we in terms of this whole path with pursuing ARM on HPC. So first, let's talk about Vanguard. This is sort of a new approach that the DOE and the NNSA is trying. Essentially, we have sort of two spectrums historically. We have a lot of test beds. If you sell interesting hardware, we're probably going to procure some of it in a test bed and try to see if we can make this work. Tens to hundreds of nodes, nothing really huge, and really we try to have a wide breadth of architectures. This takes brave users and even more brave administrators to really stand these machines up. But they're not really used for production workloads. On the other side, I think the DOE is most famous for sort of their ATS, but also CTS platforms. These are very large leadership class procurements, and they are meant for production cycles. The most quintessential or classic ATS systems that you've probably heard of would be the Trinity system that we procure with Los Alamos and the Sierra system at Lawrence Livermore. So this is really meant for a broad use case and truly day one production use. So Vanguard is sort of this idea of bridging that gap, going from 10 nodes to, maybe 10,000. And there's a whole lot that we want to sort of do in this space. Astra is just the first iteration of the Vanguard program. We expect this to be long running because I think we've had a lot of success in this approach. And really the idea is to sort of field prototype sort of machines at a scale that is interesting, but not so much that it's going to bankrupt us if this doesn't work on day one. And really be big enough to sort of garner some larger attention from our user base as well. So, all right, what is Astra? It's, basically 2,500 and change HPE Apollo 70 compute nodes with the Cavium now Marvell, Thunder X2, ARM CPUs. These are the 28-core versions, so different SKU than probably some people have seen with the 32 nodes. Each node has 128 gigabytes of DDR. The important part here is that this is done through 8 channels of DDR per socket. And that's going to lead to a lot of memory bandwidth, and that pays dividends, and I'll give a little more information on that. We're using Mellanox, EDR, InfiniBand, this is ConnectX-5, and you'll notice that this is using the socket direct, so each socket has direct 8x PCIe lanes to each socket from the IV card. And then we have a fairly significant all-flash SSD Lustre storage system on the back end. That's since been upgraded to almost a petabyte now. So, and we can push some pretty serious bandwidth with this. You know, we've sustained well over 200 gigabytes a second. So here's a quick picture of the, you know, the actual node itself. So each one of those nodes goes into, 4 of them go into 2U chassis. That 2U chassis, you have 18 of those per rack, and then we have 36 racks, and that makes up all of Astra. We also have 3 major IB spline switches for 1-to-1 at the top of the network hierarchy, and then a 2-to-1 taper from there. So, and here's a picture of my colleague, you know, Kevin Pedretti unplugging an MPI, or unplugging an InfiniBand cable and killing an MPI job on me. So, thanks, Kevin. So, this is interesting, and this will probably seem like a very long timeline for anybody not familiar with working with the US government. We're actually really proud of this. This was a really, really hastily put together plan, and we went from 0 to 100 really quickly with this in terms of the whole government aspect. You know, we started really releasing an RFP back in late 2017, and just a couple months later, we had hardware on our doorstep at the end of the fiscal year. We also, if you look down at the bottom, you'll see that there's some interesting things that happen. The hardware arrived. Can you guys see my mouse? Okay, yeah. The installation was completed, and then the facility was completed. We literally built a brand new building to put this machine in. And that wasn't done for a little while we actually had the machine. So we had to run around with yellow vests and hard hats for a while while they certified the building, which was rather fun to build try to boot your first ARM supercomputer in that environment. And then we started just running HPL and HPCG. You know, I think it was mentioned earlier by Brent that, you know, it's 156 now on the top 500. Hooray, that's good for the top 500. In all reality, HPL does not match the workloads that we actually care about. What we care far more about as a sort of benchmark proxy is HPCG, conjugate gradient. And here you can see a stark difference between HPL and HPCG. This machine was 29th on the top 500 for HPCG. And that's something that we're really proud of, as it shows that this machine design is actually meeting what we need to from a hardware standpoint. So HPL is fun. It's good to, you know, tell your congressional members, hey, yes, it's such and such fast, but you know, that connection with mission has long since been lost. So. All right, so that's a quick, dirty overview of Astra itself. Let's dive in a little bit into the software stack. So this is sort of a quick picture of our full system software stack from the ground up. We originally worked from HPE software stack as well as OpenHPC in this case. And you can see that there's this really interesting mix between you know, open source software, vendor proprietary software, third-party libraries, et cetera, et cetera. And there's a lot of sort of, you know, devilish details in here. But again, there's the entire Mellanox OFED and MOFED stack as well. So, and this is built on RHEL 7. So first, let's talk about HPCM. This is HPE's cluster manager. This was sort of this weird amalgamation between SGI and HPE's cluster deployment mechanisms. And was a brand new product as well with the initial delivery of Astra. So that was fun. The good news is it actually works, and works pretty well. It uses a set of leader nodes to boot, so 1 leader node to 288 nodes, or a scalable unit, with failover and redundancy as well. So if one of the leader nodes kicks the bucket, you can still boot your entire supercomputer. And in the past couple of months, we've demonstrated that we can boot all 2,500 or basically 2,600 nodes in less than 10 minutes. So that's kind of cool. That's of course the soft reboot. That's not from ground, from power off. So you got to boot the leader nodes and the switches themselves first. But it's still, you know, if you've actually tried to boot that many nodes at one time, that's actually fairly impressive, and we're happy with that. The other thing that we've really added into the HPCM is the ability to deploy TOS. TOS, who's actually heard of TOS? Okay, John, you don't count, but all right. So TOS, basically, for all intents and purposes, TOS is Red Hat, with a bunch of DOE NNSA stuff sprinkled on top. It's managed originally and out of Lawrence Livermore, and it is based entirely on RHEL, or in this case, RHEL 7. We've leveraged some of the work that's been done in Red Hat directly to support ARM64, and there's a whole bunch of specially tailored packages as well. And there's over 200 specific to just TOS. So this is nice because we get to customize this to our liking and to our needs, while also still relying on Red Hat for support. So while we say RHEL here, really this is TOS. So just the fact that it's slightly different did add an extra bit of challenges for us over the years, or over the past year. So there's also been a lot of Lustre enablement that's happened. You know, Lustre client on ARM was a big unknown for a while. Turns out that does work. We do see some bugs. We've also had a lot of, you know, random other issues with our Lustre deployment over the years, or over the year. But it does work, and it works at scale. And that's really nice. We've also debugged a whole lot of kernel issues over the past year or so. And these are not your typical errors. This is sort of something that's really unique to large-scale systems. It's one thing to acquire a dozen or so nodes and do some testing, but these are weird bugs that we saw only when tested at this scale. For instance, this K-worker CPU hang, basically 1 out of every 100 nodes after doing a large memory access would just go out to lunch and spin forever until you rebooted it. So this actually was fixed in upstream Linux, but not in RHEL, and we got a lot of that stuff backported through TOS. So there's several other issues that, you know, we found over the years and have fixed, but really the story here is that you've got to go actually build these things at scale to go and find these really gnarly bugs that really only exist when you put everything together in a large-scale system. So this isn't stuff that you would find, or rarely would you find just you know, building a dozen or so nodes. So we also leverage the ARM Alinea Studio and all the ARM compilers and performance libraries. I'm sure everybody's probably aware of a lot of this, but those are really important tools moving forward. We also have HPE MPI as well as OpenMPI. This is HPE's, it used to be SGI or MPT, but it's a proprietary MPI that dates way, way back. From compiler standpoint, basically we're also, you know, we have a mix of GNU 7. This is really just GCC 7.2, really to match the Sierra system, as well as the ARM Clang and Flang tools. So, and within ATSE itself, we build the full cross product of all of those, and really have done a lot of testing on this. So, what's this actually look like? Well, at the end of the day, it looks like every other cluster that you've ever logged into on a supercomputing resource. We provide modules. It looks like Red Hat. And life goes on. We've actually tested this ATSE stack and added a lot of special bits along the way to especially target the ThunderX2 CPU. This matters for some libraries more than others, specifically like OpenBLAS, where there's a significant difference in performance between what you pull off the shelf through OpenHPC versus what you actually get when you recompile for the target architecture, in this case, ThunderX2. In the future, so we've leveraged OpenHPC pretty heavily in the past, and that has been done through Linaro. In the future, we'd like to move a lot of this to SPAC, which is a new sort of HPC package management tool. There's a lot of value there for building sort of that cross product of stacks, and also now supporting binary builds. So we're looking at moving to this, and there's a lot of future work that we'd like to do in terms of leveraging lightweight and multi-kernels, specifically Rekin's MC kernel effort. We're in the process of deploying and testing that now. So this entire software stack is also put in a container. We went and built this on, you know, this little Marvel ThunderX2 node that I squirreled away and hid in a totally separate place. And I can build my entire ATSE software stack. I can push that to my local container registry. And then I can deploy that directly on Astra across all 2,500 nodes using Singularity. And this has actually turned out to be really cool because we were able to fast forward our ATSE stack to the next version and test it out in a container before actually going and deploying it. So we were able to make sure that we weren't going to break You know, our upgraded TPLs basically didn't break some of our core binaries and some of our apps that depended on this. This is a really good sort of way to test case this and to do this at scale rather than just one node on the side. So kind of a cool story, and I'll show a little bit more of that. This is really important. If you think you can stand up a system of this size and not have a good idea what's actually going on and monitoring all the power and all the telemetry data at real time, you're kidding yourself. These are really necessary tools that we had to quickly whip up from scratch. And you know, just to quickly show you, you could see some of the power traces here and the difference between HPL and stream. But this is sort of always an afterthought when we come to build HPC, and that's a shame because you really don't want me playing peekaboo in the system trying to fix whatever's going on. You really need that telemetry data from day one. So that's sort of a fun little lesson learned there. All right, so now I get to talk a little bit about some of the application results. And this is sort of, you know, the start of a whole lot more, but I'm hoping I can show a little bit here. So there's some peak system performance considerations here. There's a quick comparison chart between various Intel CTS and our Trinity system, which is a mixture of both Haswell and Knights Landing, as well as the current Sierra system. And you know, on paper, it doesn't look like anything special. However, you know, the real key part that we're going to leverage here is the memory bandwidth. So that's just kind of a quick summary comparing the actual architectures. But this doesn't always translate to real-world application performance, as we're finding. So first, there's SPARC. SPARC is sort of the new Sandia's leading hypersonic CFD code. This is a really important code and developed under our new ATDM program. And we have been able to deploy this successfully in sort of a production-like environment, running really interesting problems on Astra already, and scaling this out to 2,000 nodes. So this is essentially a mixture of, this is a whole lot of partial differential equations, so there's a lot of assemble and solve phases. And we've compiled this across both GCC and the ARM tools. And we see performance varies a little bit here back and forth. It depends on various compiler flags as well, but this is really promising performance for us to see. There's also, somebody told me this really nice story about the compiler situation at ARM, where one side of the building is GCC and the other side of the building is the ARM tools, and I think they compete back and forth. I haven't seen this directly, but I think that's a really good sign. We want to encourage that sort of diversity and that support for multiple different compilers moving forward with ARM, because that becomes really important. So we also took the same app and deployed it in a container using our ATSE stack that I just described. And we ran this, in this case you can see me just scaling this out to 1,000 nodes, but we've scaled it out to 2,000 nodes as well. And we're getting near native performance running on a container with Astra on an ARM 64 machine compared to native. I accidentally put in some compiler optimizations and made my container run slightly faster, but that's just because it was easy enough for me to quickly tweak a couple of things, rebuild my third-party libraries, and deploy it with a container before actually going and reconfiguring my entire ATSE stack. So that's kind of cool. Another really important app is Empire. This is a particle and cell code. And here we're directly comparing sort of Trinity and the scaling of Trinity to Astra. And you can see these things essentially, okay, that's a little tough to see, sorry for the eye chart, but essentially these look very similar, and that's a good thing. We are seeing that we can scale this across very large problems, sort of our quote-unquote XL problem at scale. And we can actually do that with half as many nodes because we can bin pack that problem into a smaller set of nodes compared to our Trinity deployment. So the fact that we're seeing similar scaling here and a little bit better performance, it varies depending on problem size, but this is good. This is really good news for us. We also looked at CTH. This is sort of the world's leading shock physics hydro code. It's a purely Fortran, well, okay, 90+% of it is Fortran. It's actually a very old code. But it uses a mix of Fortran 4 and Fortran 90, and we are able to compile this and run this on Astra, and as you can see, scale to over 2,000 nodes. And we're getting significantly better performance than we had seen with our Trinity system. So, and a lot of this has to do with leveraging the ARM flying tools, but we also did eventually get it to compile in GCC as well. So this is a totally different application now. This is sort of some of our emerging workload that we're starting to see across the tri-labs and really the DOE as a whole, this new notion of AI. This is specifically a reinforcement learning, which is a little different than sort of the unsupervised sort of and deep neural nets that you see, but I think it's a really interesting use case, and I think I can play this. Yeah, basically this is just literally trying to, a genetic algorithm to try to teach, you know, how to play a game and how to learn to walk. So this is essentially a nice toy tool that's available publicly, but we were able to deploy it on Astra, scaling it to a couple hundred nodes, and leveraging some of the parallelism of this code. The key thing to take away here is that we're really starting to play with this. This was also deployed in a container, and a lot of the lessons that we can take from this sort of open code directly apply to some of our mission multi-objective optimization problems that we see and are tooling along with our simulations. So, all right. We ported a whole lot of applications. I showed you guys just a couple of quick ones, but you know, you name it, we've probably deployed it. The key takeaway here is I'm not talking about proxy applications. I'm not talking about mini apps. I'm talking about millions and millions of lines of code that have deployed and running at scale. That is a huge step forward than where we were just a year ago. And that's sort of the real take-home thing. We've actually been a little too successful, and they've speeded up our schedule a little bit, so the machine basically is disappearing now for all intents and purposes and will be used for production codes for the remainder of its lifetime. That's great, but you know, annoying at the same time for all the R&D work that I also wanted to do. But this really, yeah, great. Nice discount, right? So yeah, that really shows that we've been successful, much to our own surprise even, that we really do have a lot of this working. That being said, I don't know if we're quite done. Are we really there yet, right? Yes, we have a lot of the basic components already in place. You know, we've got an InfiniBand stack that works. We can leverage multiple MPI frameworks. We can use the Lustre client. It'd be nice to have the Lustre server so I can have a purely ARM architecture the next time I buy one of these. We have Slurm working. These are sort of, there's a lot of the basic components of deploying a true HPC supercomputer that we have in place working in what is now essentially about to be a production environment. And the compilers and math libraries do work sufficiently well. We can run these codes. That's great. And we're starting to see that a lot of the performance is incredibly competitive with the latest that you can go and buy off the shelf from Intel or whoever else have you. And the nice thing is there's a nice range and diversity across integrators. With HPE buying Cray, maybe that decreases a little bit for us, but this is still good news. I think we have a lot of diversity in the overall HPC ecosystem. And while we talk about HPC making billion-dollar investments, this is still a niche market in the grand scheme of things. So the more diversity that we can encourage, the better. We're not done though. Astra in no way tried to look at SVE. We were unable to prove that in the time frame that we had. So there's still a lot of work to be done there, and I think we're going to see that through our friends in Japan, and we're really excited for that upcoming evaluation. There's still a lot of tuning and a lot of performance optimization that we can do that we've kind of left on the table for right now. We need better threading and vectorization of some of these kernels, and we still need a lot more work to be done on profilers and debuggers and ensuring memory correctness. And there's a lot of, I think, future work that we can leverage on sort of standardization for performance counters and energy and whatnot. So I'd like to try to encourage that to some extent. So this is sort of a very quickly evolving and interesting conversation. We plan on continuing this actually at SC19. So I'm going to give a quick pitch for this BOF that we have at SC19 with John Linford, myself, really trying to discuss whether or not ARM can take the lead in HPC. I think you know where my answer is, but this is sort of going to be a fun discussion that we're going to have and continue at SC. So if you're an HPC nerd and you're coming to supercomputing, please join us Tuesday. So with that, I'll end and take any questions. I was told there was a mic. You had a question, right? I was told there was a microphone somewhere.
Really good presentation. Question I got there, just at a high level, because I know you just said at the very end you don't have a standard counter for energy consumption, but compared to the other systems you were running those applications at, what was your power consumption as a base load against the other ones just in this raw form you have now? We're not optimizing threads, we're not doing any of those things yet that could probably really improve that scale, but just have you seen a reduction, or is it just an even sort of a cost metric?
The more you optimize your codes, the higher the amount of power that you're going to use, right? So the wall plate power for this system is 1.3 megawatts. I mean, that's enough to power a couple thousand homes. So, but it's not that much in the grand scheme of what we're about to build within the DOE. We've seen anywhere from 1.2 real world to, you know, half of that to you know, 600 kilowatts. So it varies heavily on code, right? The power profile of one code will be totally different than another code. So it's hard to really answer that question quantitatively. What we'd like to do is have a better sort of set of tools that we can use to really sort of control power as well. For instance, I may have the opportunity to know my large MPI code is going to do this really big all-to-all communication and going to go do this big all-reduce across 100,000 cores, right? That happens literally in these codes. It'd be nice to just, you know, downclock the CPU and save a little energy while that happens, while we do this all-to-all reduce. There's other phases where we really need to drive memory bandwidth, and we don't have to have that CPU at full tilt. So wouldn't it be nice to sort of tune that back a little bit to save energy? So that's sort of some of the R&D directions that we're hoping to go over the next year with this system, and we're starting to get better at tooling for that. But it'd be nice to have a standard way to do this across any HPC architecture, whether that's, you know, an Intel or ARM 64 system, right? So, any other questions? Oh, come on, you guys are easy.
On the same topic, so does it mean you run all the CPUs at the same frequency all the time and disable dynamic frequency scaling as well as static CPU frequency scaling?
You could do a lot of different things.
What do you do at the moment?
Well, right now, the default on Astra is we leave it at the 2 gigahertz clock, and we leave the memory frequency set at a different clock, right? Yep. In the future, it'd be nice to have a little more variation in that. For instance, when you may have a reduction or a per node reduction that happens on one node. You've got to condense 56 MPI tasks down to one that then goes out to the network. You may want to, boy, it would be nice if I could turbo that one core and put the rest of them to sleep, right? There's a lot of really interesting opportunities that we should be able to take advantage of, and we're just starting to get there. And we've barely been able to do that on Intel architectures. But when we start talking about, you know, 30, 40, 50 megawatts, these become really critical capabilities for us. So, all right, cool. Thanks, everybody.